Population growth and ongoing urbanization puts enormous pressure on cities. 75% of the infrastructure required by 2050 still needs to be built. This demonstration illustrates how infrastructure professionals can use Bentley technology to increase productivity, to meet their needs and shape sustainable and resilient cities of the future. We describe a typical urban situation in the vicinity of a main road, where our AI-powered digital twin platform is instrumental to ensure data is always enriched in iTwins and connected across the infrastructure lifecycle. Our openness supports urban innovation by connecting data and people. To describe the current state and help the city administration to identify investment priorities in context with existing infrastructure, different layers of open and relevant data are pulled together. In addition to the impact of the influx of residents, climate change is a major factor in the urban agenda. Using simple 2D urban heat maps for 3D rendering helps to identify heat islands, here seen in dark red. To improve the microclimate, a very effective urban planning measure is to integrate more trees. The deep blue area confirms a lack of vegetation where it's hot. Intensive rainfalls have led to an overloaded drainage network, which results in flooding. To analyze the root cause, our software helps professionals to identify the correlations and bottlenecks. Another socio-economic driven input to urban planning are land values, which also depend on accessibility of city districts. Through our mobility solutions, we uncover demands in the given neighborhood, as illustrated in the bar stack. It highlights the purpose of travel, such as work commute, shopping, or school drop-off. High-resolution mobility modeling capabilities can then be applied to estimate the volume of trips and predict the impact of traffic and the investments in transportation infrastructure. Informed with such baseline data, urban planners can improve their decision-making by superimposing contextual information in the digital twin, such as reality models for the brownfield environment, combined with 3D city models and subsurface utilities either in 2D or in 3D coming from CAD or BIM. In addition, consumption of IFC files or native files like Revit for buildings is available in the iTwin, including electrical and structural data with the ability to navigate inside a building and identify any engineering elements. Since there is no loss of data, all asset and engineering information is accessible. All involved stakeholders can make decisions based on proposed and active projects through a single lens with engineering-grade fidelity. Our main road leads to an underdeveloped site where the city wants to place a public cultural center. The former time-consuming iteration to find the best option within infrastructure constraints can now be streamlined applying AI. AI allows us to quickly explore feasible alternatives, considering context information such as zoning and building codes, for which the engineer uses an AI copilot, as you see here. Then the application uses parametric design tools to quickly create a site plan, and again the designer communicates with the tool through the copilot. That reacts to even more tasks like find optimal space for parking lots or minimize earthwork. In this conceptual design phase, the digital twin is used as a means of consultation and review. City leaders need tools like this to communicate in an inclusive way. The iTwin allows engineering models to be seamlessly shared, combining architecture engineering-oriented high-fidelity output with interactional virtual reality. This allows citizens to experience different design alternatives and provide real-time feedback. In the following detailed design stage, prime contractors can quickly consolidate multidisciplinary designs from different contractors and review conflicts that are identified, raise and track issues, and collaborate effectively in real time. In the design of the main road, a clash between different underground utilities has been identified and notified to respective parties. The seamless data-driven workflow between the reviewer and the designer allows the designer to immediately visualize the issue. Here, the designer can review the comments from project managers in their relevant design applications without the need for file transfer. He can fix the issue without delay, which leads to cost savings in the project. During this collaboration process, project managers have a complete audit trail, which allows them to more easily compare design changes against previous versions, report on progress, and effectively track relevant KPIs. With the platform ability to quickly aggregate multiple models and projects into design applications, designers have the necessary capabilities to create resilient designs. Here we see the subway project in conjunction with the reconstruction of the major avenue. Key engineering components and the bill of materials of the subway is accessible. Overlaying CAD and BIM with reality models provide better context and visualization. Since the model already has material information, the designer can early enough ascertain the embodied carbon content while designing. This creates not only efficiency in the overall design process, but also allows traceability and governance for the owner-operator in addressing their net zero targets. As the city is running multiple projects, involved departments have the possibility to navigate to any project design seamlessly with an immersive experience. Check relevant documentation or metrics to follow through with administrative procedures such as payments or financial reporting. A feeder road to the main avenue is currently affected by a bridge construction site. Logistics, site security, and the impact on traffic becomes manageable based on material information in the construction schedule in the iTwin. Project managers can track the health of the project, identify potential delays and other negative impacts in advance. Again, our software enables the transition from detailed design to construction without any loss of information. The iTwin is further enriched with data which allows prime contractors and owner-operators to virtually rehearse and minimize negative impacts on projects and citizens. For operational purposes, the iTwins from design is now accessible and is federated with operational and maintenance data. For example, the chargers for electrical vehicles that were designed in the main avenue are now connected with real-time IoT data. Since street assets such as lights and poles need to be maintained, there is a demand to efficiently capture, record and analyze these assets dynamically, driven by asset inventory, maintenance and safety policies. And this up-to-date asset information is especially important for emergency response. Enriched iTwins can help here tremendously. For example, as hazardous zones are visualized, these are immediately augmented with necessary safety information coming from IoT devices, street maps, and 360 images, enhancing the readiness for blue light services. During an emergency response, the location of personnel is tracked, giving the operator full insight of the event to give commands accordingly. Using the given infrastructure context in an iTwin, our mobility solution can simulate how people will behave during an emergency situation. Cities are responsible for logistics and safety and need to prepare for evacuations. In this example, we see how people will gather as they exit the subway. Cities face challenging times, but it is in cities where innovation and growth happens. Digitalization is an essential process to future-proof cities. In our open AI-powered digital twin platform, enhanced with immersive visualization capabilities, is the means to empower infrastructure professionals and stakeholders to align on targets across the lifecycle and achieve more with less.